Hi everyone. In the last lecture, we have discussed about the Gelfand map for commutative unital Banach algebras. Today, we are going to discuss about representation of commutative unital C-star algebras. So, we have earlier defined what a C-star algebra is, and we have discussed some examples also. The two important examples we discussed about C-star algebras are A equal to C of K. K is compact and Hausdorff space. Okay, here the involution is f going to f bar, and the norm of f is the sup norm. This is a C star norm. And the second example we discussed about b of h a equal to b of h, where h is a Hilbert space, of course complex Hilbert space. Here the involution is t going to t star, and norm is the C star norm is nothing but the operator norm. Norm of t is supreme of norm tx, where x is coming from x, with norm of x equal to 1. Okay. Now let us look at few important properties of C-star algebras and elements of C-star algebras. So let A be a unital C-star algebra. Then A is said to be A in A is said to be self-adjoint if A equal to A star. A is said to be normal if A star A equal to A star, and unitary if A star A equal to A star, that is 1. 1 is the unit element of A. So we say A to be positive if A equal to A star and the spectrum of A is contained in the positive real line. A projection, in fact here orthogonal projection, if A equal to A star, that equal to A square. So we have seen all these definitions when T is in B of H, but this is a generalization of uh, operators. Okay, now let us look at some important spectral properties of self-adjoint elements. Theorem. Let A be a unital C-star algebra and A in A be self-adjoint. Then we can show that spectral radius of A and norm of A are same. Earlier we have shown that if T is a normal operator, then a spectral radius of T and norm of T are same. So here we want to prove it for self-adjoint elements. In fact, this result can be extended to normal elements in a system algebra. So let us look at the proof. Okay, if A equal to A star, then we have norm of A square by the C star condition. This is norm of A star A, but that is nothing but norm A square because A star equal to A. Now, if you look at A square is also self-adjoint element also. So if I look at A power 2 power n, this is also self-adjoint. So hence we can conclude that norm of A power 2 power n is exactly norm of A power 2 power n. Now by the spectral radius formula, we can conclude that spectral radius of A is limit n tends to infinity norm of A power n whole power 1 by n, but now we are looking at a subsequence, so this is also sufficient 1 by 2 power n. So this is 1. Sorry, this is norm A. Okay. So this completes the proof when A is self-adjoint. When A is normal, so remark A is normal, then also we can say that spectral radius of A equal to norm of A. So we have norm of A star A, because A star is self-adjoint, this is norm of spectral radius of A star A. For commuting element, if A and B are two commuting elements, spectral radius of AB less than or equal to spectral radius of A into spectral radius of B. So if you use this result, you will get this one. This is nothing but spectral radius of, again spectral radius of A and spectral radius of A star are same. So we have used two things. If AB is in A with AB equal to BA, then spectral radius of AB is less than or equal to spectral radius of A into spectral radius of B. Spectral radius of A star, by definition this can be shown easily, that's equal to spectral radius of A. So we use these two results to conclude. But left hand side we have this is nothing but norm of A square by the C star condition. But anyway, this is again spectral radius norm of A square. So therefore we can say that spectral radius of A and norm of A are same when A is normal. One important consequence of this result is the following. If A is a star, A is an algebra with an involution, then there exists unique norm which makes A into a C star algebra. Here we have the following observation. Norm of A star A, this is norm A square, this is supremum spectral radius of A star A. This is supreme of mod lambda, lambda in the spectrum of A star A. Now if there are two norms which make this star algebra to be a C star algebra, then they also satisfy, these two norms satisfy this condition. Those two norms are same. So this is a proof. Okay. So next we want to prove that if A is a self-adjoint element, the spectrum is always subset of R. So theorem, let A be a unital C star algebra and A in A is self-adjoint. Then we can conclude that spectrum of A is subset of R. Assume that spectrum of if there is a complex number in the spectrum of A, we show that the imaginary part is 0. So let us take C equal to A plus IB. So let us write this as X. Let us take X is an element of A. Write C equal to A plus IB, where A and B are real numbers. This is a part of spectrum of X. Then we can say that X minus C into 1 is not invertible. Now define an element like Xn as X minus A into 1 plus I into NB. Now if you look at Xn minus I n plus 1 into B, that is nothing. So B into 1 here. Xn is X minus A into 1 plus INB minus INB into 1 minus IB. So this is X minus A plus IB. So this is X minus C. This is not invertible. So this implies that I into n plus 1 into B, this is in the spectrum of Xn for every n. So from this we can conclude that, so this implies, we know that an element of the spectrum in modulus less than or equal to the spectral radius. So this implies modulus, so n plus 1 whole square into b square, this is modulus of I into n plus 1b mod square. This is less than or equal to spectral radius of xn square. So this is less than or equal to norm of xn square, because spectral radius is always less than or equal to the norm. This is nothing but norm of xn star xn. Now if you compute norm of xn star xn, you will get this as norm of x minus a into 1 whole square plus n square b square. Okay. So from this we can conclude that, so here left hand side n square plus 2n plus 1, but n square is, so you will get 2n plus 1 into b square is less than or equal to, by triangle inequality you can say norm minus x minus a whole square. This is for every n. Now from this we can say that b must be 0, because left hand side depends on n, whereas the right hand side does not depend on n. So therefore C equal to A in the spectrum of X. So we can conclude that spectrum of X is subset of R. Okay. Next, one more important result, let us quickly recall. So we have shown that if t is in B of h, then t can be written as a plus ib, where a is self-adjoint and b is also self-adjoint. Now the same result we can prove for elements in the C-star algebra theorem. Let A be a unital C-star algebra and A be an element of A. Or you can say that X is an element of A. Then X can be written as x1 plus ix2, where x1, x2 are in A are self-adjoint. In fact, this representation is unique. This is similar to the earlier result we proved for bounded operators. The proof is similar. So write x1 as x plus x star by 2 and x2 as x minus x star by 2i. So check that x1 star is x1 and x2 star is x2, also x as x1 plus ix2. The uniqueness part can be proved in a easy way, similar to the bounded operators case. Okay, so this is about uh, the Cartesian decomposition of an element in a C-star algebra. So this is called the Cartesian decomposition. Next, we are interested in representation of C-star algebras, which are commutative. So let us look at C-star homomorphism. So let us define C-star homomorphisms. Okay. Let A and B be unital C-star algebras with units 1A and 1B respectively. A map phi from A into B is called a C-star homomorphism if phi is linear, that is phi of x plus alpha y is phi x plus alpha of phi y for every xy in A, alpha in C. Phi is multiplicative, that is phi of xy is phi x multiplied by phi y. The third condition is phi preserves the involution. Phi of x star is phi of x whole star for every x in x, and phi preserves the identity. Phi of 1a is 1b. If these conditions are satisfied, then phi is said to be C star homomorphism. If phi is 1 to 1, that is called C star isomorphism. If phi is 1 to 1 and onto, then we can say that A and B are C star isomorphic onto. So if phi is in addition, phi is 1 to 1, then phi is called a C star isomorphism. If there exists, if phi is also onto, then we say A and B are A is C star isomer onto. A is C star isomorphic onto B. Okay. Now let us look at one simple example. Okay, let us take A to be a unital C star algebra. So define a map eta from A into A direct sum A. We can check that this is a direct sum of two C star algebras is a C star algebra. You send A into A00. We can show that. So this is C star isomorph. C star isomorphism. A and A direct sum A are C star isomorphic. So we can easily check that this map satisfies all the conditions of C star isomorphism. For example, its linear multiplicativity is seen easily. Preserving the adjoint also is seen easily, and it maps identity into identity. One is mapped to 1001, which is a identity element in or unit element in A direct sum A. But this is not onto map because elements of A direct sum A are of the form A00B. So it cannot be onto. Okay. So the next one is, let us fix a unitary element. Define y from A into A by x go into u star xu for every x in A. We can easily show that this is C star isomorphism as well as onto. That can be worked out easily. Okay. So let us look at some important properties of C star homomorphism. So let A and B be unital C star algebras, and phi from A into B be a C star homomorphism. Then we can say that spectrum of phi of A with respect to the algebra is contained in spectrum of A, and not only that, norm of phi of A is less than or equal to norm of A for every A in A. That means it's a contraction. So we know the first one already we have proved earlier when we discussed about multiplicative maps. So this already done. So let us look at proof of 2. So let us look at norm of phi of a square. This is norm of phi of a star phi of a. This is nothing but this is positive. This is self-adjoint element. So this is spectral radius of phi of a star phi of a. So this is nothing but spectral radius of phi of a star a. We know that spectrum of phi of a star a is contained in spectrum of a star a. So this is less than or equal to spectral radius of a star a. But a star a is a self-adjoint element. This is equal to norm of a star a, and this is equal to norm a square. So therefore norm of phi of a is less than or equal to norm of a for every a in a. Okay. Now so if phi is also onto, if phi is a bijection, we can say that the spectrums are preserved. So corollary, if phi from A into B is a C star homomorphism, and bijective, then we can say that spectrum of phi of A with respect to B is exactly spectrum of A with respect to A, and we can show that here norm of phi of A is an isometry as well as onto, because when phi is invertible, it's also a C star homomorphism. Now the result follows from the earlier result that we have proved. Okay, this is about C star homomorphisms. Now we want to look at representation of commutative C star algebra. Let A be a unital commutative C star algebra. Then there exist. Then A is C star isomorphic with C of k for some compact Hausdorff space. More precisely, the Gelfand map gamma from A into C of MA is C star isomorphism and also onto. In fact, we also show that it is C star isometric. Okay, the proof is, so we know that gamma is multiplicative. Okay, so our claim is to show that gamma of x star is gamma f whole star. Let us take x is in A, then we can write x as x1 plus ix2, where x1 equal to x1 star and x2 equal to x2 star. These are self-adjoint elements in A. So then we have gamma of x is gamma of x1 plus gamma x2 star is gamma x1 minus ix2, because x1 minus ix2. This is gamma x1 minus I gamma x2, because gamma is linear. Now x1 is self-adjoint, and spectrum of x1 is subset of R, and we know that gamma of x1, spectrum of x1 is exactly range of gamma 1, gamma x1. Spectrum of x1 is range of gamma x1. So this is true for x2 also. That means gamma x1 is in R, gamma x2 also is element of R. So we can say that this is gamma x1 plus I gamma x2 whole bar. So this is gamma x whole bar. Okay. So this proves the that gamma preserves the involution. Okay. Next we want to show that gamma is isometric. So next claim, gamma is an isometry. Okay. So let us take x in A, then if you look at gamma x whole square, this is subnorm, this is gamma x star gamma x, norm of this. Now this is nothing but gamma of x star x okay. Now gamma x star x is a real valued function. Now this is exactly norm of x star x. This we have already seen earlier, and this is nothing but norm of x square. So therefore norm of gamma x is norm of x for every x in x. So this says that for every x in A, this says that gamma is an isometry. Okay. Now we want to show that gamma is also onto gamma is. So since gamma is an isometry, gamma of A, which is subset of C of MA, is closed as gamma is an isometry. Okay. Now we want to show that gamma A is self-adjoint. So let us take B equal to gamma A in gamma. Then we have B star is gamma A whole bar. This is gamma A star by the earlier observation that we made. So this is again in gamma of A. So that means whenever B is in gamma A, B star is also gamma A. We can say B star is also in gamma A. We can say that gamma is self-adjoint, and gamma A contains all constant functions, because gamma of 1 of A is 1 in this is a constant function, 1 of y is phi of 1, that is 1. So it maps constant functions into constant functions. So gamma A contains constant functions. We also want to show that gamma separates points of MA. So claim gamma separates points of MA. That means if we take two elements phi 1, phi 2 in MA. So let us take phi 1, phi 2 in MA such that phi 1 not equal to phi 2. Then there exists A in A such that phi 1 of A is not equal to phi 2 of A. Or we can say that gamma of A at phi 1 is not equal to gamma A at phi 2. So whenever we have two distinct elements in M suffix A, that is phi 1 not equal to phi 2, then we were able to show that gamma A phi 1 is not equal to gamma A phi 2. That means there exists a continuous function on MA such that function evaluated phi 1 phi 2 are different. So this we can say that gamma separates points of MA. Now by applying the Stone-Weierstrass theorem, you can say that gamma A is dense in C of MA, but we know that gamma A is closed. So therefore gamma A is C of MA. So that means gamma is onto. So we have shown that gamma is 1 1 onto, and it's also isometry. So it also preserves the involution of A. So it is C star isometric isomorphism onto. So we cannot distinguish A and C of MA. Okay. So this completes the proof of the representative theorem of commutative C star algebra. So this result is known as Gelfand-Neumark theorem. Okay. So in the case of Banach algebras, we were able to show that gamma uh, is a map from A into C of MA. It's we can embed A into C of MA as a subalgebra only, but here we are getting more properties, namely it is isometric as well as onto. Okay, so with this result, actually we can discuss many important results, namely, for example, we know if A is an element of a C-star algebra and P is a polynomial, then P of A is defined without any ambiguity. Now, if F is a continuous function on the spectrum of an element A in the C-star algebra, then we can also define F of A using this Gelfand map. We can discuss continuous functions of element in C-star algebras when A is a normal element. So that is known as continuous functional calculus. So we will be discussing those results at a later stage. I will stop here. Thank you very much.